to go ahead and talk about basically one last concept, and then we'll go into a review for your final. I mean, this is the final exam of your final block of your didactic experience, at least. So, what I want to do is I want to talk about radiation real quick. So radiation's something that you're not likely to encounter for the most part, but you're really not likely to encounter a significant radiation incident as an EMS provider. Certainly historically, it's not particularly likely. Obviously, we encounter radiation in our everyday lives, right? Because, radiation is just what? Anything that radiates, basically anything that radiates energy, right? So radiation these lights are radiating, right? They're radiating electromagnetic waves of energy. But it's not just radiation that we're worried about, it's really a certain type of radiation called ionizing radiation that we're most concerned about. Ionizing radiation. And this is radiation that has enough energy to ionize, to ionize atoms and molecules. And what does it mean to ionize something?
To change the electrons of that?
Right, so basically it means to knock an electron off of something, right? Or if it's a molecule, we're talking about a chemical bond, it breaks the chemical bond by ionizing the electron involved in that, right? So its radiation has enough energy to basically turn atoms and molecules into ions. Well, that, as you might imagine, is really bad if those atoms and molecules happen to be within our cells and tissues, right? So ionizing radiation is actually a type of trauma, if you want to look at it that way, right? Because what we talk about, trauma is simply when the amount of energy delivered to the tissues of the body, that energy is enough to overcome the energy with the potential energy of the chemical bonds that hold those tissues together, right? And this could be in the form of penetrating trauma, blunt trauma, burn trauma, right? Cold injuries as well, and also ionizing radiation is a very specialized form of trauma. Does that kind of make sense there? You guys okay with that? Okay, so now that we've identified the problem, there are three major things that you guys have to know. Okay, you have to know basically how to attenuate or minimize the damage caused by a potential incident involving radioactive materials, ionizing radiation. And what are those three principles?
Time, distance, shield.
Good. Is everyone okay with that? Basically this is the foundation of protecting yourself is time. What do we mean by time?
The amount of time spent.
Right. Decrease the amount of time that your patient, whatever, is exposed to that environment, right? What do we mean by distance?
Get further away from the source.
Good. We maximize the distance. Good. And then shielding, what do we mean by that?
Something that's
Concrete or water.
Good. You want to put as much mass between you and whatever the problem is as possible, right?
What is the second one thing?
Maximize, right? Maximize distance, right? So these are the three principles going into it: time, distance, and shielding. But what I want to do is I want to just go into just a little bit of nuance. So we're going to talk a little bit about health physics, if you will. Nothing too bad, but what we need to understand is why these things are important. And so imagine that I have a point source of ionizing radiation. Okay, maybe it's a pellet of plutonium, right? And that plutonium is spewing out alpha particles, okay, as plutonium. Certain you guys are familiar with the term isotope?
Mm-hmm.
We talked about that in chemistry. What is an isotope?
It's a different amount of protons.
Protons are the fingerprint, right? So if I have one proton, for example, in the nucleus of an atom, that makes it what? That makes it hydrogen, right? Two protons would make it Helium,
Right.
3 protons would make it lithium, et cetera, right? Neutrons, right? So 1 proton by itself is a hydrogen, right? It's a hydrogen ion. But what if I had a proton and a neutron, which is neutrally charged, it has about the same mass as a proton?
Isotope.
That's an isotope of hydrogen, right? It's still hydrogen, but it's an isotope of hydrogen, and that's something called deuterium. And then if I had 1 proton and 2 neutrons, okay, that is yet another isotope of hydrogen known as tritium. And you guys may be familiar with tritium, huh?
Yeah.
Because tritium is commonly found in watches and in gun sights. Why?
Because it
Gives
goes
off.
on.
Gives off.
Right. So isotopes can be less stable than their parent atom, right? For example, a hydrogen atom with just a proton is very stable, right? It's not going to decay, it's not going to turn into anything else. But the more neutrons you start adding into that nucleus, the bigger the nucleus gets, right? And the force, there's something called the strong force that kind of holds the nucleus together. It gets spread out, it gets weaker and weaker, and the nucleus becomes more unstable. And so isotopes that have more neutrons tend to be more and more unstable, which is why you can take tritium, which is just hydrogen, right? That's all tritium is it's hydrogen with 2 extra neutrons. And then the nucleus of the tritium is unstable and it breaks down. And when it breaks down, the energy that is released from the breakdown, okay, of that nucleus, some of that energy is released in visible light. And that is that glow that you can see. Does that make sense? Other things like radium, for example, unstable isotopes of radium can glow as well. Does that kind of make sense? So there you go, right? You learn something new, right? A tritium gun is nothing more than a really heavy isotope of hydrogen. Cool. All right. So isotopes are important because isotopes are created in certain nuclear reactions, in nuclear reactors and nuclear fission and fusion explosions. Not so much dirty explosions, but anywhere where you're messing around with the nucleus of an atom. And reactors are really good at taking things that are not necessarily unstable. And because lots of neutrons are made in nuclear reactors, those neutrons bombard other atoms and can turn them into isotopes, which are then unstable and can become radioactive and radiate. But they're much more dangerous than tritium because they can radiate energies that are much higher than visible light. They can radiate alpha particles, beta particles, gamma rays, in some cases, X-rays, etc. Okay, you guys cool with that? Okay, so that was kind of an aside, but so let's say I have a point source here, okay? And let's say that I am 1 meter away from that source of radiation, right? Okay, so I'm 1 meter away. So this point source is, and let's just kind of keep it simple. Let's just like put it in the center of this room, okay? And let's just assume there's no air in the room because that just makes math a lot easier, right? Because once you have air, then you have to make the math work out, you have to take into account that the molecules in the air is going to absorb some of that radiation, and so that's what we call an attenuation coefficient or factor. So then we have to add an attenuation factor in there. But let's just keep it simple, right? So I have a point source, and it's going to radiate in every direction. You guys cool with that? All right. But let's say that I'm a meter. I'm within a meter, okay, within a radius. You guys know what radius is, right? Radius is from the center, it's a chord, from the center of the circle out to the circumference, right? So let's say that I have a radius of 1 meter, okay? So I'm 1 meter away. The amount of radiation that's going to hit me is going to be fairly significant. Would you guys agree? But let's say that I'm now 2 meters away. Okay, what has happened?
Increased it.
It's kind of spread out, hasn't it? And there is more area for that radiation to kind of diffuse into, if you will, right? And does anyone know what the area of a circle is? How do we figure out the area of a circle?
It's a radius pi squared, is that right? Radius squared?
Sort of, yeah, it's pi, right? It's
Times
pi
squared.
r squared, right?
That's,
That's the radius of the circle, and then cubed is the volume, but we'll just stick with radius. It just keeps it simple. Okay, so let's find the radius of a circle if I'm 1 meter away, okay?
stand by.
So that's 1, my radius is 1, so what would the area be of that circle? Well, what's-
Area or circumference?
So it's 3.14.
Huh?
Area or circumference?
Area.
So it's 3.14.
So pi is 3.14 times 1 squared. What's 1 squared? 1. So that's going to be 3.14 square meters, right? So that radiation, you want to think about it, is kind of diffusing out into an area of 3.3 square meters, right? Where that should be a volume. But again, we're keeping the math simple, right? You guys cool with that?
I think I know where this is going.
All right. So now let's say that I move another meter away. So I'm now 2 meters away from that source, okay? Well, pi is 3.14 times 2 squared. What's 2 squared? 4. What's 3 times 4? 12 squared. So now that radiation is diffusing into a much larger area, and let's move yet another meter away.
Should be another 4, right?
Right, so 3 times, what's 3 squared? 9. What's 3 times 9?
19.
Huh?
Oh, wait, 3 times
No,
9 is
27. 27 square meter area. So do you see how this is spreading out? And it is not spreading out in a linear fashion, is it? It's basically, if the basic relationship, if you just set pi to 1 because it's a constant, the basic relationship is it spreads out by the square of the radius, or the square of the distance you are away from that radioactive point. Does that kind of make sense? Now, we can make it more complicated, we can throw in a cube and all that, but does that generally make sense?
They teach you if you double the distance, the starting point
Yeah.
drops by a factor of 4.
Yeah,
That's how they
more
teach
or
you.
less, yeah.
Which that
Yeah.
proves it right there.
Yeah, 3, 12, 27, more or less 4-ish, right? Does that make sense? Oh no, that damn math stuff, right? Okay, so this is why distance is so important. And of course, shielding is going to be important, because if you have more stuff between you and that, okay, that attenuation coefficient is going to go up, right? More of that radiation is going to get absorbed before it gets to you, okay? And then obviously, time is pretty important, right? Minimize the amount of time you are in that environment. Okay, you guys cool with that? All right, so now what I want to do is I want to go deep. I want to make sense of this stuff. And the reason that I want to make a little bit of sense of this stuff is there's a lot of fear around this, okay? And we occasionally do have incidents involving radiation. And there's a lot of fear in being able to articulate what's going on to people and to explain things to people can actually attenuate a lot of that fear. So, with that in mind, I want to spend just a little bit of time talking about the terminology that we encounter, okay? Because there's a lot of terminology and we see this. Okay, so first of all, let's go back to our source of radiation. So we here have some source of radiation, right? And there are 2 terms that we use to describe how quickly or how much that source is radiating, or the rate, what we call the rate of radioactive emission, okay? So the rate of emission of radioactivity coming from that source. You guys okay so far? So that's the rate of emission. Okay. there are two concepts that we use to describe that. The first one is what we call the Curie. Okay? The Curie. Okay? The Curie is what we say, or what is known as the non-SI unit. Okay? You guys are familiar with SI units, right? Right? You should be. The SI units tend to be the standard units that everybody agrees upon, whereas the non-SI units tend to be a bit more not necessarily ad hoc, but not everybody agrees on using them, right? So, everybody in the world pretty much uses a metric system, right? Yeah, except certain countries, right, use inches versus meters, right? Everybody can agree on meters, not necessarily everyone can agree on yards, right? Okay, it's kind of the same thing, right? The SI units are standard units that pretty much everybody agrees upon, and then your non-SI units are units that certain people use, okay? The SI unit is something known as a becquerel. It's B-E, something like that, becquerel, that's the SI unit. Actually, it only has one L in it. E-L, the becquerel, okay? Now, we don't have to know what the units are. Okay, that's not as important for this class. You know, how much emission is, what is 1 Curie, what is 1 becquerel. Okay, we don't necessarily have to know that, but that's just what those words mean. Okay, does that make sense? But is that necessarily helpful for us from a clinical standpoint?
No.
Well, not necessarily, right? So once that radiation, once that radioactivity gets out, well, that's kind of important, right? Okay, because we're not necessarily focused on how much is emitted, but once it gets emitted and it's out in the environment, that's kind of important, right? So once the radiation gets beyond the source, what is the general amount of radiation you have in the environment? Okay, so emitted or in the environment, we'll say. Okay, in the environment. So this is talking about emitting from a certain specific source, and this is, okay, now what do I have in the environment that I'm working in, presumably? You guys okay with that? There are two terms. There are what we call the rentigens. The rentigen, R-O-E-N-T. Rentigen, I believe, is how that's spelled. Okay, that tends to be the non-SI, and then the SI unit is coulombs per kilogram. Coulombs per kilogram. There may be a -1 in there, but whatever. Okay. Again, is that the most helpful thing, though? What do you think the most helpful measure of radiation is going to be?
Rate of exposure.
How much you actually get exposed to, right? How much is actually getting absorbed into your body? That's what we really want to know. So as you might imagine, guess what? There are also two terms that we use to describe how much an object actually absorbs. Okay, how much is actually absorbed? Okay, and the standard unit that we currently use, okay, or the two standard units are the grays, or we call it gray, or GY, okay, and then the rad. Okay, radiation absorbed dose is what that stands for. Okay, the rad. And the difference between a gray and a rad is just a conversion factor. 1 gray, GY, equals 100 rads. Okay, 1 gray equals 100 rads. You guys okay with that? Okay. Okay, so you're okay with what a rad is and what a gray is? Okay, so it gets even more complicated. Sorry. So, I now look at this thing. Okay, I have rads. Okay, we know what a rad is, right? But the rad is a measure of the total absorbed dose. Okay? Here's the problem. Not all radiation is the same. Okay? So throw some different types of radioactive things at me. Okay, so we've got alpha particles. Okay, we've got beta particles. We've got gamma. What else?
X-rays.
We've got X-rays and neutrons. All right, neutrons. All right, so alpha and beta are what we call proper particles. These are pieces of nuclei. An alpha particle is nothing more than ionized helium. So it's a helium atom without its electrons. So it's a chunk of a nucleus that is decayed. Okay? So alpha particles tend to be heavy, right? They tend not to go very far though, because they are so massive, they tend not to move very far, right? They're heavy, they don't move very far, and do they penetrate very deeply? No, they have very limited penetration power, right? A beta particle, okay, a beta particle is basically an electron that gets ejected. It's a high energy electron that gets ejected from the nucleus, okay? So it has less mass than an alpha particle, it's moving fast, and so its ability to penetrate is further, right? It's higher, and its ability to move further is enhanced as well. And then gamma rays and X-rays are actually electromagnetic radiation, right? High energy electromagnetic radiation. X-rays have a little less energy than gamma rays, right? And these can move very far, right? And then they can penetrate very deeply. Okay, so if I get exposed to 100 rads of X-rays, for example, that exposure is probably going to be different than if I get exposed to 100 rads of alpha particles. Does that make sense? All right. So what we really want to know is what is the equivalent dose, right? And there is a term known as the REM, R-E-M, the Rentgen equivalency in man. Okay? And basically what we have to do is we figure out the rads. Okay? How many rads, okay, did you absorb? Okay? So what's your rads? And then you multiply that by a factor, okay? A quality factor called Q. And the quality factor is what kind of radiation are we exposed to here, right? And then that equals REM. Okay? Are you guys cool with that? All right, so in general, X-rays, beta particles, so X-rays, gamma, and beta have a quality factor of 1. So it's pretty much a 1-to-1 conversion, where 100 rads of X-rays is going to be about 100 REM. Does that make sense? Okay, but this is where it kind of gets tricky. Neutrons. Okay, neutrons have a quality factor of about 3 to 10, I believe. Okay, or 3 to 20. 3 to 20. Depending on what's going on. And then alpha particles have a quality factor of 20. So what does that mean? So if I get exposed to 100 rads of alpha particles, what's my equivalent?
5 again.
Huh?
It would be 5 gamma, right?
Well, no.
No, it would be.
What would my REM?
2,000,
It would be 2,000 REM, my equivalency. So what does that mean? If I were to compare alpha exposure and gamma exposure,
It's 20 times.
it's 20 times worse. Does that make sense? And I don't know if you guys have ever learned this before. For the most part, people learn, alpha particles are weak and they can't penetrate, not a big deal, right? Guess what? They are weak, they cannot penetrate very well. But if you manage to get exposed to alpha radiation, it is much more deadly than gamma rays. Equivalent dose, right? Why is that?
Well, I think because alpha's mostly ingested.
Well, because, the major route of exposure is going to be inhalation and ingestion. And because you're talking about a nucleus of a helium atom that has lost its electrons. So what do you think that wants to do?
Grab the electron.
It wants to grab electrons, and it will tear those electrons at any cost from your tissues, right? It is highly ionizing. Gamma rays, on the other hand, have much more energy than alpha, right? But a gamma ray can pass right through your body and never interact with an electron, right? Because, believe it or not, most of everything is empty space. Most of everything is empty space. If I were in like a large lecture hall, and I were to take like the nucleus of, say, a hydrogen atom, and so imagine a large lecture hall at MSU, and I were to stand in the center of that, and I were to say that this was approximately the nucleus, that electron, okay, that one electron in that hydrogen atom would basically occupy the entire lecture hall around that one thing, right? And so basically the entire atom is nothing but empty space. So when I get exposed to gamma rays, X-rays, okay, and to some extent beta particles, it's very likely that that gamma ray can pass right through that atom and never interact with the electron, never hit the nucleus, never hit the electron, right? Because most of our bodies, isn't that weird to think about it? That most everything is empty space? And it's actually the fields, right? It's actually the electrical fields and the electrical repulsion, electrostatic repulsion that kind of creates this illusion, if you will, that there's actually something there, right? Is that kind of weird, isn't it? Right? So it's quite likely that these can just pass right through without ionizing. Whereas alpha and to a large extent neutrons are much larger, much more massive, and the chance that they're going to actually interact with something is going to be a lot higher because they're so much larger. Does that kind of make sense? Okay, so that is why these things are so much worse. But remember, when it comes to protecting yourself from these different things, shielding, right, is going to be a lot easier with alpha particles, right?
Yeah.
So you could wear a protective suit, for example, right? If you were like in a fully encapsulated suit, right? What level would that be? A level A, right? If you were in a level A suit, alpha particles would not be a big deal, right? Right? But what if I was in a level A suit, fully encapsulated, and it was a significant gamma source?
So right.
It's just going to go right through that suit, right? Okay, so these are going to be much worse, okay, when it comes to shielding, right? It's going to be much harder to shield these. It's going to be a lot easier to shield these, but your absorbed dose, your equivalency, is going to be a lot more problematic when it comes to alpha versus gamma. If you're looking at the same total absorbed dose, that's a big thing, right? The total, okay, so 100 rads of absorbed, that's a big thing, absorbed. If I absorb 100 rads of gamma and 100 rads of alpha, okay, the equivalency is going to be much higher on the alpha. Now that's not really how it works in real life. You know, you absorb some gamma and some alpha, depending on the situation, but does that make sense there, what's going on? Okay. And I think understanding the terminology is a little helpful when you're talking to people. You know, if they're saying, oh my God, it's 1,000,000 curies at the reactor, what's going on? It's the end of the world. Okay, well, wait a minute. Okay, I understand that's the rate of emission, but what we're most concerned about is how much is the body actually absorbing. And clinically, this is what you need to understand is clinically what means what, okay? So clinically, when we talk about absorption, we can talk about it in terms of RADS or RIM, and I'm just going to talk about it in terms of RADS, even though we understand that there is a quality factor that we have to use to convert RADS to RIM. Okay, you guys cool with that? Okay, so let's talk about these. So when we are in the low range of absorption, so somewhere around 75 to 125 RADS. All right. This tends to be fairly low, and we're talking acute exposure here. We're not talking about over 20 years. We're talking about an acute, boom, I just get hit with 75 to 125 RADS. Okay, this dosing range tends to be associated with minimal effects. Okay, patients typically don't even get sick. This is where you see minor changes occur with your blood. Okay, and remember, it is the rapidly dividing cells that are affected worse, right? Because the DNA is unraveled from the histones, it's open, it's unprotected, right? And those hydrogen bonds can get blasted around, and et cetera, okay? So rapidly dividing cells are affected first, right? And so does that surprise anybody? That's going to be your blood, right? Because that's where you have lots of cell division occurring in your marrow, okay? Now, at 125 to 200 RADS, RIM, okay, this is where we start moving into acute radiation sickness territory, okay? Now, in this range, are these signs and symptoms going to be sudden? If I get hit with 200 RADS, am I suddenly going to develop these? No, right? I'm not. This is going to take a little bit of time. So there may be a period of time where your patient appears clinically normal. Okay, they appear okay. And then over hours to days to weeks, they can have these signs and symptoms appear. And these, of course, are going to be associated with, where are you at? Are you closer to the 125 or closer to the 200? But in general, what kinds of side effects are we going to see? So our blood's getting hit. What else is rapidly dividing going to get hit?
Cells of reproduction.
Okay, reproductive cells, right? So your spermatozoa are going to take a hit, right? Sperm counts are going to go down. You're going to have problems with the ovum, the ova rather, right? Okay, what else? Clinically, think clinical signs and symptoms. Good, GI, right? You have rapidly dividing cells in your gastrointestinal tract. So you're going to have nausea, vomiting, bleeding, and what else? Where else do we have lots of rapidly dividing cells? Brain is like the slowest. Hair loss. Yeah. So nausea, vomiting, bleeding, hair loss, immunosuppression, blood changes. These are characteristic findings associated with acute radiation sickness. You guys okay with that? All right. So 125 to 200 is where we start seeing that classic acute radiation sickness occur, but it's not immediate, right? This can take some time to develop. All right. And then we move into the 200 to 600 range. All right. 200 to 600 range. Okay. This is definitely acute radiation sickness, and in this range, death, acute death, within days of that exposure is going to be more likely. And in general, the LD50, all things equal, is about 400. Okay, the LD50 is right around 400. Okay, if you get exposed about 400 RADS or RIM. All right. You guys okay with that? And then if we have a massive dose of radiation, this is generally going to be over 600. What do you suppose is going to happen with 600 plus?
Death.
Death, right? And what are the signs and symptoms going to do?
They're dead.
Was it immediate though? It's not necessarily immediate death, but the signs and symptoms will suddenly occur. So if you're taking care of somebody who's involved in some radiation exposure incident, and let's say that incident happened 20 minutes ago, all right? They pull them out of whatever, they start decontaminating them, and now you're taking care of that patient. They're vomiting, okay, they're bleeding, their hair's starting to fall out. What does that tell you?
They're gonna die.
They're
That
at
large
600
dose.
plus.
Large
Yeah. Now, they may have the same signs and symptoms of someone who got hit with 200 rads, right? Right? But what's the major thing differentiating between, say, 200 and 1,000?
Time.
The time of onset, right? If it is sudden or relatively sudden onset signs and symptoms, that indicates a massive exposure, right? Whereas if, let's say they present a week after some incident with nausea and vomiting, hair loss, that's gonna tell you, okay, we're more in this range here, right? Does that kind of make sense? All right, you guys good with that? All right, so that's just some basic health physics stuff for you there. Okay, cool. Excellent. All right, so I think that's all I want to talk about. Now, let's get into the review for your final. How does that sound?